同城传译。So, welcome back. So the last two keynote speakers for this Congress, as I said earlier in Chinese, so most both who two gentlemen that who come from a long way from the United States. And I suppose the two gentlemen, of course, are no stranger to many of you in the room, because both of them are leading professors in the broad area of artificial intelligence. So the next speaker, 我的中文英文混着讲。The next speaker is Professor Rao Kamapati. I hope the name is correctly pronounced. So Professor Kamapati is a professor at Arizona State University. And he has primary research interest in artificial intelligence, and also planning and decision making, and also interested in data and information integration, and also social media analysis. So Rao, if I may call you Rao, is the recipient of several awards for both his research and teaching, including Best and Influential Paper Award. I should in particular mention that he is the program chair of the just recently concluded International Joint Conference on Artificial Intelligence, that is EduCap 2016, which was held in New York last month. His talk today is on challenges in planning for human-robot cohabitation. 这就是我昨天讲到的人机共治。So without further ado, ladies and gentlemen, welcome Rao, please.
Thank you all, and thank you CCAI for inviting me. I assume people can hear me. So I'm Rao Kamapati, and I guess the most important thing is my WeChat is Bara2Z. That's pretty much the only thing you need to know, right? I mean, I realize that in China that's all matters. So I did make my WeChat account. And anyway, I'm going to talk about, as I said, human-machine collaboration. And then actually there is like a sub-theme which is in praise of human-aware AI. So actually, as you'll see in a minute, I will be looking at two parts of the talk. The first part is sort of more general in terms of why it is important to think about the challenges of human-aware artificial intelligence systems. And the second part is more specific to my research program on how to do some of these, what are some of these challenges in the context of planning and decision making. Okay, so that's what I'll try to do. So first I want to mention that I've been here both yesterday and today. I don't know how many of you know Rosetta Stone. Rosetta Stone is the way we figured out what Egyptian hieroglyphics actually mean. So I was trying to run this experiment since I know AI. And I'm hearing, yesterday there was no actual translation, so I was only hearing Chinese speakers and I know AI. I was trying to see if I can do Rosetta Stone and learn Chinese yesterday by just comparing the notes. So I could give this talk in Chinese. Unfortunately, that's not going to happen. I did not learn too many words beyond actually, I think, Jige and of course, Ni Hao. So I will stick to English. So clearly the very first thing AI still needs to do is a babble fish. As some of you who might know from the Hitchhiker's Guide to Galaxy, you need a babble fish that you can put in your ear so that every language can be translated to every other language dynamically. Great. So one other thing I want to mention before I get into the specifics of my talk is I'm also here partly sort of representing CCAI, even though mostly I'm representing my own research. So I just want to set one slide to talk about CCAI and the China AI community. Of course, researchers from China are a very formidable force in AI itself and in CCAI. One of the top countries in terms of the number of submissions as well as the number of acceptances for the last several years in both CCAI and ICCAI has been China. And I think some of you might know that CCAI 17 by mistake wound up being put on the dates of the Year of the Rooster. And when we realized that, oh my God, it's not going to be good news because we won't have half the conference because you guys are not going to travel. So right away it got changed, even though it was actually a big penalty. It was very important because I believe that China is a really big part of AI community and definitely CCAI. So I'm here to say just this one thing that I want, as the president of CCAI, to the extent I have any authority here, I really would like to see much more prominent representation of China in CCAI. We already have lots and lots of papers submitted. I actually want lots and lots of members, lots and lots of people serving on the council, lots and lots of people being fellows of CCAI, so that I think it will be great to have a thriving international AI community. So I am very much a big fan of that idea, and in fact, I'm spending a couple more days here having other meetings with various people to make this happen. So that's one thing, and actually Chang Yang, who is a good friend of mine from early grad school days, he's now on the council. I want a lot more representation. Okay, so that's all I want to actually say about CCAI. Of course, CCAI conference itself is in San Francisco. I'm pretty sure all of you are writing papers in the back. Okay, so the agenda for my talk today is part one. I want to sort of argue that the path to general AI, path to the serious artificial intelligence, goes through human-machine collaboration. And I want to say that, in fact, it's a good thing. It's not cheating the problem of AI. It is, in fact, trying to make the problem of AI more broader and, in fact, taking it back to the roots of the Holy Quest. And then I also, in the second part, I will speak about some of the specific challenges such human-aware AI will bring to automated planning and decision making. Okay, so that's basically my agenda. So, I'm very old, and it turns out that this was my bachelor's thesis back in 1983. Probably 90% of this audience hasn't been born then. So I was working at that time in speech recognition, and what drew me to AI is this idea that essentially we are really talking about one of the three fundamental problems facing humanity, fundamental challenges that are still left open: origin of the universe, origin of the life, and nature of intelligence. In fact, I sneak peeked into Tomaso's talk next, and this point that, in fact, we are trying to understand, many of us got into AI not to just make deep learning algorithms, but actually to understand the nature of intelligence. What better way to do it than actually try to develop algorithms that will show intelligent behavior. So when my students made a mistake of picking me to give a last lecture, I wound up giving a last lecture on the lessons of AI to everyday life. And in fact, and so I'm sort of a dyed-in-the-wool AI aficionado. One interesting thing, of course, is when I started working in AI, it was a very different time. Most of my graduate student time, the outside perception on AI was very much combative. Okay, I kind of think of this as physicists and philosophers united against AI. It can't be done. Okay, so all the British physicists were busy writing papers and books. For example, Roger Penrose on Emperor's New Mind, saying, "Are you guys crazy? You should not be even working on this. It's not possible. Mind our machine." Hubert Dreyfus saying, "Computers still can't do," and of course the great Chinese room puzzle. So you can imagine that most of my time I was just sort of lurking in the background thinking, let's leave me alone. We are interested in these problems. If you don't want to do it, that's fine, but we are interested in working on that. Now, around that time, one of the other things that happened actually for AI as an area is we started talking about the enterprise of AI in somewhat narrower terms, about not basically, we sort of moved away from cognitive science, philosophy, and started talking about specific algorithms that will show narrow intelligent behavior, and that was the thing that we were doing. Okay, that was great. So of course things have changed. Obviously, even around 2007 onwards, people started saying things are working in AI, we have to start feeling worried, when we start paying attention. Now of course, the way public perception goes is while the progress in AI goes like this, public perception will go like that, right? That's the usual normal nonlinear phenomena. And so back in 2014, I actually remember when I got elected to be the CCAI president, it was a nice and happy time where basically some people interested in technical issues of AI were working on that. And then Elon Musk shows up at MIT, and basically when asked what do you think is the biggest problem facing humanity, he said the thing that keeps you awake is not Tesla cars running amok, but actually AI, evil AI, and the threats and safety issues posed by AI. And of course then Stephen Hawking also mentioned something about that. Next thing you know, we started seeing in public media this whole idea of robots running amok and taking over the world. Okay, of course we go from 0 to infinity very fast, right? So of course then people started screaming, and then one of the interesting things, of course, is everybody is an expert in AI. It turns out you don't actually have to do an intro to AI to actually talk about what is and is not possible about AI. So Musk and Wozniak are worried about AI. There are some serious issues such as AI and technological unemployment. Reid Hoffman, who is a Netflix guy, basically also has an opinion about AI. And of course, Stephen Hawking starts still worrying. And when I keep looking at this, as I mentioned, I started into AI at a time when people are saying, what the heck are you doing? You should be doing something more useful. And suddenly I went from there to being the head of a mafia gang. And people are supposed to pay me money to protect the world. Okay, so it looked as if this guy, Oscar Wilde, who once said, America seems to be the only country that went from barbarism to decadence without civilization in between. Obviously, Oscar Wilde would not be allowed if Trump becomes president. But the interesting thing is, I started thinking, is AI is the only technology that's going from disappointment to doomsday without touching beneficial in the middle? Okay, obviously not, but when you look at what's going on in the world, it looks as if that's sort of some of the issues that are going on. Now, I personally am not worried because I think we can take these robots one by one. I don't know how many of you know the hitchhiker robot, which tried to go from place to place, hitchhiking that way. And when it came to Philadelphia, the city of brotherly love, we know that these robots are up to no good, so we did that to that robot. We killed the heck out of it. Right. The other thing we can do is build a big wall. When we get a new president in the US, we might be building lots of walls. So we might build one wall for the robots too. But the more serious point I want to make of this whole paranoia about the big threats of AI is AI in general has had a curious ambivalence to humans. Okay, do we want humans in the loop with the AI systems, or do we want to kind of replace them? In general, AI has this idea of replace versus augment trade-off. And so our systems have been happiest either far away from humans, such as on Mars, where I haven't yet seen any humans, or on the Nevada deserts, where the cars would be running around but without any humans, or even RoboSoccer, where essentially we are taking adversarial tone. So the question then is, what happened to coexistence? Why aren't we designing machines that work with humans as against sort of replace them? And every time we celebrate something about AI, we celebrate the fact that yet another thing that humans can do, machines do better. So we already know we don't have to play chess, we don't have to play Jeopardy, we also don't have to play Go. So I don't know what we're going to do. Okay, but the interesting question is, from the beginnings of AI, some people at least have been thinking about this idea of coexistence. In fact, McCarthy's original idea was advice taker, a system that works with humans and takes advice. And Janet Kalodner, this researcher, gets based reasoning, and says, please realize that, don't accuse me of sexism. She said that everybody needs a good housewife, in the sense that you need somebody who takes care of all your problems, okay? And even, of course, if you think of HAL, the 2001 Space Odyssey, you need some system. Even there, it was sort of a human-aware system which is working in conjunction with humans. So why don't we get more interest in human-aware AI? That's something that I want you to think about, and I want to also bring up this issue that right after we think about humans in the loop, human and AI systems and humans working together, there is this worry that maybe putting the humans is a way of cheating the problem, to make the problem easier. And it's not surprising, because the original mechanical Turk, not the one that Amazon runs, but the original mechanical Turk was this machine, quote-unquote machine, that used to play chess, but there was an actual person inside the machine who was playing the chess, right? So anytime you put humans in the loop, you're cheating, okay? So it is sort of possible that you would start wondering, maybe human-aware AI is sort of diluting the goal of AI. And what I really want to argue, in some sense, the big point I want you to take out of my talk is no. That in fact, human-aware AI expands the reach and scope of the AI enterprise. It indeed brings very interesting research challenges, many of which we have very carefully pushed under the mat because we never had to deal with humans before. And also, on the side, it reduces some of these off-the-top worries about AI. If you design a world where robots work with humans, they're much less likely to take over the world. Okay? So why wouldn't you invent a future that why would we want to invent a future where we would actually have no control? Okay, so the other thing that I want to mention is just a high-level point of intelligence is we know that there are many different kinds of intelligence, right? There is perceptual and manipulation intelligence that even little kids have, and then you have cognitive and reasoning intelligence, and then of course there is emotional and social intelligence. These things we write. When I teach this, when I talk about this in my class, I say, oh, emotional intelligence is this stuff the men among you apparently don't have, and the social intelligence is the thing that the engineers among you probably don't have. But the more important thing is, there isn't much work, we didn't have to think about those aspects of intelligence. In fact, if you know the old Rodney Dangerfield, is this a comedian in the US, he used to talk about, I don't get no respect. Emotional intelligence and social intelligence never got any respect from the AI systems because we were never actually working with humans. But if you want systems to work with humans, they better have those qualities. Okay, the way you get mad at your colleague is not necessarily because they're stupid. In fact, we can deal with stupid people. We can't deal with people who are clueless in terms of social skills. We can't deal with people who don't have an emotional response to things that are happening. And so if you suddenly have an AI system interacting with you and it doesn't have these intelligence aspects, then you're going to be mad. And so if you bring those back in, then that is broadening the reach of AI systems, right? The other thing is actually, if you have taken Intro to AI, especially with like Russell and Narvik's book, we typically talk about the 4 different goals of AI, and the systems that think like humans, systems that think rationally, systems that act like humans, systems that act rationally, and we pretty much dismiss the whole humans aspect. And the first lecture of AI is to say, really AI is about systems that think rationally. We don't need to care about acting or thinking like humans. And that thinking like humans is the stuff of intelligent tutoring systems and cognitive science, and acting like humans, God knows who cares. But honestly, if you have systems working with humans, they better act like humans. The jury is still out on whether or not emotions help our performance. But you can't deal with entities that don't have emotions. Okay, so an AI system working in tandem with humans winds up having to have emotional responses and social intelligence. And in fact, there are many studies showing that interfaces that even show certain amount of the ability to act like humans become much more usable. Okay, so once again, this brings together this sort of issues that we have pushed under the mat. The other thing, if you're into box diagrams and intelligent agent design, this is the picture that you see in Intro to AI for intelligent agent design. He's an agent which is dealing with the environment, and it's trying to get sensors, and it's basically keeping track of the state of the world. Now the interesting thing is, if this environment also has humans, then you can just say humans are just yet another obstacle that we need to get around, but we really want to help them as an agent. You need essentially to keep track of the mental state of the human in the loop. And that winds up changing the architecture quite significantly. It turns out that, I'm just showing something that I'm going to quickly go over, but really every piece of your agent architecture now is going to be significantly harder, because now you're keeping track of the mental states of the humans in the loop, and that's stuff that you have to learn oftentimes. Okay. So once again, this is my argument that putting the humans in the loop is not cheating the problem; it's making the problem harder. And you want to make the problem harder because that's the future that we want to design, not the future where we have no use and the robots are taking over the world. And so, in fact, there is like a bunch of cases here. Recently at DARPA, there's been a lot more interest in talking about the collaborating with machines and the challenges that come. DARPA is this research agency in the US. we made a bunch of pretty significantly hard cases where human-machine collaboration will open up large number of challenges. So for example, you have the machine has to be able to predict what the human is going to do, need to have an idea of the human's capabilities, should be able to mitigate the risk for the human, should be able to anticipate the humans, should have some sense of the normative behaviors that are expected in teams, should have the ability to coordinate based on their understanding, the machine's understanding of what humans might be thinking, should be able to revise its beliefs, should be able to infer mental state, should be able to understand whether or not the human in the loop is little too tired and maybe needs more help, should be able to do social regulation and also activity coordination through shared mental models. I'm not expecting you to read this. If you read this fast, I'm very impressed with your reading skills. But these are actually, most of these are open problems. To supporting these sorts of capabilities is really quite beyond the systems that we work on right now. And aside, there is this continuing debate in AI about symbols versus neurons, right? The original AI physical symbol system hypothesis by Newell and Simon essentially said a physical symbol system has the necessary and sufficient means for general intelligence. That's why much of the AI technology went with declarative representations for the longest time. Okay. On the other hand, you have Jeff Hinton, who has been standing in the back rows, now of course in the front rows, but standing in the back rows and saying, you don't need symbols. We don't have symbols necessarily, we have neurons. So symbols, actually, he said in his turn of phrase, are just luminiferous ether of AI. Ether being the stuff that people invented, talk about whether the waves will propagate in a medium. Okay. Now that is an interesting debate. We can get involved in that, but the bigger point ultimately is interpretable AI is very important. Okay. The one big problem with deep learning systems, the neural systems, is when they reach a decision, they're not very good at explaining why they reached that decision. It is true that we are thinking the basis for biological intelligence is neurons. However, an important thing that we do is we are able to explain why we did something, and when I'm talking to you, most of the time it's essentially a declarative interaction. It's not some sort of a USB wire from my head to your head. Okay? Maybe we'll get to that, but right now that's not where we are. And if systems are working with humans, then we do need to care about interpretability of the decisions that they're doing. It's not just whether they are able to explain their behaviors, but they should be even more proactive. They should be showing behaviors that don't need explanation to begin with. Right now I'm giving a talk to you. If I start jumping around and start singing, then I have to unnecessarily explain why I am singing. So I avoid doing that because that's not what you're expecting of me. And if I have to show inexplicable behavior, then I should be able to give you signaling and I should be able to explain why I'm doing that. Okay, so for all these reasons, actually, these are sort of high-level reasons of human-aware AI and the challenges in them. One of the things that I did, as was mentioned earlier, I was the program chair for International Joint Conference on AI that just got over in New York. Maybe some of you were there. Actually, lots and lots of people from China were there. The factoid is that the country with the largest number of paper submissions was China in that conference, and it was just 1 or 2 papers less than the US in terms of the number of papers accepted. So, but China was a close second. But the more important thing is, for the special theme of that conference, we chose human-aware AI. Of course, I was running the show, so I probably had something to do with it. But I really believe that it was not just my pet project. It is something I hope I try to convince you that this is broadening the scope of AI. It brings in large number of additional challenges that you want to be able to take into account. Okay, so that's basically the first part. Part one is that indeed, in fact, you want to be interested in human-aware and collaborative systems, and it's not cheating, it actually makes life much more interesting. That's what I tried to say in the first part. Okay, now the second part is planning challenges. So of course, this stuff is kind of high level. You may want to know, when I had this whole number of case studies, what actual challenges, what technical challenges are there in terms of making that kind of coordination happen. And I'm a planning guy, originally, for the longest time, I've been working in automated planning and decision making. And of course, agents working with us should be able to actually do actions and plans, because it's not just enough to be able to label examples. And so one of the things I've been looking at is what are the challenges that human-aware AI brings to automated planning. Okay, so that's what I'll try to do in my remaining time. Of course, this part is more technical than the previous one, but it's also going to be faster, so even faster than what I was speaking already. I'm already being told, please speak slowly, but I'm from South India, and South India, this is the slowest we can speak. Okay. Okay, so there is the robot. This is the usual robot in the environment scenario, and the reason I show this is the most important thing for any agent is the $1 million, a gazillion $billion question is what action to do next, which is essentially planning. You're planning what action to do next. So to me, I think that the whole point of AI is to support planning. Okay. Now, of course, the original traditional planning essentially sort of simplified the problem by saying, imagine you already know the planner is all by itself, the agent is all by itself, and it knows everything that it needs to know about the world. So the model has been handwritten, the goals are fully specified, and the world state is known. Then just figure out what sequence of actions you have to do to reach the goal state. This is what if you take Intro to AI, you hear this as classical planning, and there's a problem. And that problem, as simple as it is, it's already computationally hard. It turns out to be a piece-based hard problem. Okay. Now, the thing that you want to keep in mind is, of course, after the planner is done, it just assumes that it doesn't need to deal with anything else. There are a whole bunch of assumptions, complete descriptions of the model, fully specified preferences, objects in the worlds are known upfront, one-shot planning. This basically makes planning a pure inference problem. One of the interesting things that AI people have done for the longest time is to make silos. These are the learning people. They learn and won't use the knowledge that they learn. These are the planning people. They'll assume that the knowledge is given and they'll only do inference. Now, of course, overall intelligence requires the ability to learn the models and use them, right? But humans in the loop really can ruin a perfect day. These are just some more simple scenarios where you will wind up having humans in the loop planning scenarios. Of course, anything where an agent is interacting with human is a human in the loop planning scenario. But this one is a mission planning scenario. This is a crowdsourced planning scenario where the automated planner winds up being sort of a herder of the crowds. I show these because we have done work on all of these and we have papers on this. But one other one that's kind of interesting is the idea of search and rescue scenarios where robots and humans might be working together to actually rescue people, which is sort of a nice thing to be able to do, especially, for example, in this recent earthquake sorts of scenarios. Okay. So in all these cases, the planners need to be able to at least avoid getting into the way, want to provide proactive support, and may sometimes have to take help from humans, and also definitely have to be able to team with them. And it turns out that that changes the planning problem quite significantly. There's a whole bunch of, pretty much every assumption I wrote is now violated. Models are no longer complete. It could be because actually nobody wrote down the model for you. Or more importantly, even if somebody wrote down the model about the world, the most important thing I don't know is what's going on in your head about what I am doing and what my capabilities are. So those models always have to be learned. And the preferences of the human agents would be typically quite partial, and so you will have to deal with partially specified preferences. This is sort of goes back to this whole idea of advice taker and elaborating an advice to actually solve the problem. And then package planning problem is no longer there, and planning and acting is a continual problem. Okay, so it turns out that now everything has to change because of that. This was like last year we gave a tutorial at CCAI on human in the loop planning and decision support, which was like a 4.5-hour tutorial on the different kinds of challenges that come up. And actually it's available in YouTube. I understand YouTube is not a good place to be here, but it is available. So then one of the things we did there is to point out the challenges in human-in-the-loop planning. One aspect, of course, for the planner is they need to be able to interpret what the humans are trying to do. So you're trying to recognize their goals. Goal and intent recognition becomes an important part of planning. You should be able to plan with incomplete domain models. For those of you who know anything about planning and decision making, most of that work assumes the decision model is complete. And many of the worries about safe AI are about what happens if you are trying to do optimal thing and in an incompletely known world, because that can have all sorts of unanticipated side effects, okay? So we need to worry about what to do in planning with incomplete models. And more importantly, you don't expect people to write the models for you. You should be able to learn the models that you're going to use. Now, when you're talking about learning the models, it turns out the typical models that have been used in the planning community might be too hard to learn given the amount of data that's available. So you will have to consider shallower models, which is kind of an interesting thing. On learning side, we are going from already shallower models and hopefully going towards causally supported models. On planning side, because it was a pure inference problem, it was started with causally supported models, but because they're harder to learn, you may have to go towards shallower models. So they might actually meet in the middle, okay, which is when you will have interesting systems possible. Finally, you want the system should be able to show explicable behavior, that is behavior that doesn't need too much explanation to begin with. And if there is explanation needed, it should be able to provide an explanation for that. And then finally, you want to understand engineers deciding what humans want in teaming performance is a bit of an oxymoron, because we are sort of barely human ourselves. And so we actually have to deal with human factors, researchers who have thought about how teaming works in human teams and use that to come up with the capabilities that automated planners have to support. And so these were the challenges, and essentially, obviously I'm just going to go very quickly on some of we have done work on each of these challenges. We work on incomplete domain models and a spectrum of domain models, how to learn them. We work on how to plan to be useful to the human, how to make planned behavior explicable in the loop, for the human in the loop. And finally, how to actually recognize when to provide support in this human factor sense, okay? And I'm going to just quickly go and give you some idea of what sort of work that gets done in each of those. So on the incomplete domain models, the important thing to note is if you are from the planning, or if you are aware of work in automated planning, you typically start from classical and start making the models more and more expressive. They start supporting uncertainty, they'll start supporting partial observability, and so on and so forth. It doesn't have anything to do with whether you're talking about stochastic or non-stochastic. You start with MDPs, you go to POMDPs, you go to tech POMDPs, and so on. All of them are complete models still. But if you're talking about incomplete models, you essentially have another axis, an axis where the models are incomplete in different types of ways, and you want to be able to talk about how to do planning in those cases. There you wind up having to change the solution concept for what it means to be a plan in such a model, okay? This is like a nice big colorful picture with this one showing that these are the traditional planning models, which are complete and they're completely causal models. And at the other end, we might not even have any idea of what are the actions like. And instead of being in one of the extremes, we've been looking at parts of the spectrum. So we looked at, for example, incomplete models that are very similar to traditional planning models, except some actions might be missing, preconditions or effects. We have looked at partial models called capability models, and finally we looked at things like word vectors, where all you learn is if you see this action, maybe this other action is likely to happen. You don't know why it is supposed to happen, but correlation-wise, that's expected. Now, even that sort of a shallow model can be very useful in actually being able to anticipate what humans are trying to do and be able to help them. And the important thing that this picture shows here is the shallower models are much easier to learn. They put much less demands on the kind of example traces you'll wind up needing. You don't need complete plan traces. By the time you come to shallow models, you can actually go with just partial plan traces or plan fragments with missing observations, and you can still do quite well. Okay, so I am actually going to, this one is more of the traditional planning model with incomplete preconditions and effects. It turns out to be nice and close to general AI topics, and we have done a bunch of work showing that planning in those kinds of models becomes what's called a robust planning, where an incomplete model actually is a stand-in for a variety of domain models, like an exponential number of domain models, and then you can actually compile that into different existing planning techniques such as conformant probabilistic planning, or you can also provide your own heuristics for these kinds of planning models. We have done some work on capability models I won't mention, but I do want to say a little about the action vector models, where, as I said, we are essentially using something, the kind of thing that people in information retrieval use. In fact, we wound up using the skip-gram model. In fact, my collaborator was Hansi, who's sitting there in the front row. We worked there and seeing, basically just trying to figure out whether the action affinities that are learned by word vector models can be used to support planning. This is something that people don't consider because we assume planning means complete models with preconditioned effects. The interesting thing that we showed was, in fact, given the same amount of training data, if you were to learn a shallow model instead of a complete model, you do better, which is kind of mind-blowing at some level, but if you think a little, it's because the complete model would be overfitting to the data and it winds up having bad performance. So this was some work that we just presented in AMAS 16, and it had like a nomination for the best paper. So the other thing we've done work on, of course, is how do planners plan to be useful to the humans. That involves essentially at the top level integration of plan recognition and plan generation, and we have done a variety of pieces of work there, basically including during the interaction the model of the word might be changing and the human is telling the robot, okay, here are new actions that are available to you, and how to take that into consideration. One last thing that I want to mention is planned behavior should be made explicable to the human. You don't necessarily, if you're an agent, you don't want to just consider a plan that is the most optimal for you. You also want to see what the human in the loop expects you to do and try to make the plan you are making closer to what the human expects in the loop. This is a caricature scenario where if you are expecting a robot to clean the table, under certain cost models, cleaning the table might be easiest by just throwing everything off the table. But that's not necessarily what the humans might be expecting based on their model of you. And so in some sense the robot now has to figure out what the human expects about its capabilities and make a plan that is not just optimal for itself, but it is sort of closer to what the humans wind up expecting. So this winds up being both a learning problem because now you're trying to learn what the humans think of your models, but it also becomes an optimization problem where you're not only considering the optimal plans with respect to your model, but you're also considering the distance between that plan and the plan that the user, the human, would have expected you to do, and try to make your plan closer to that. It becomes a more interesting optimization problem. We have done some interesting work on that, and actually the way you learn the model here, it turns out, is all you're talking about. This is an issue of what human thinks the robot's planning model is. This is two levels of indirection, okay? And so to understand that, you essentially, what the machine can try to do is to see and have a theory of how humans see a behavior to be explicable. In our case, we decided that one reasonable idea is that humans look at actions that are being done and see whether or not they are in support of higher level goals. And so these higher level goals are labels, and so given these sort of labeled sequential behaviors, you can learn the model underlying it. We actually learned this as CRFs in one case, and then that already gives quite a significant improvement in the kind of behavior, the plans that the robot will show. More recently, just before I left, one of my students, actually a Chinese student, did some work on using LSTM models and found that much better, you can do better than CRFs. The point is, I'm not saying deep learning is not necessary. It is that the problem is a bigger problem. It's not just a learning problem. Okay. The last thing I want to quickly mention is human factors is important. People in AI assume that we can just be everything. We can do human factors because we are engineers. But then what happens is you will have Tesla car crash. You can't just make autonomous pilot, call something autonomous pilot and say autonomous pilot is only an assistant. It will do the full driving, but you have to be completely awake the whole entire time. Which bozos in the world do it? Nobody does it. That's why, in fact, you get into accidents, okay? So there is nothing wrong with autonomous driving, but you cannot assume that people will just come from zero attention to full attention in short amount of time. This is obvious to people in human factors. If there was a human factor person around, they would probably have told this. If there was a human factors person around, they would have told Microsoft that paperclip is not a great interface, but they had to make it open and then find it the hard way. Okay, so we actually work in our work. We don't just assume that we know what humans like. We actually work with human factors researchers, and they'll wind up doing, with them we do Wizard of Oz human studies to understand how teaming behavior works, and then we try to replicate it in, make planners that will show the kind of capabilities that teaming behavior requires, and then support that, then actually go back and check, in fact, if the behavior that we are developing is useful, has been found to be useful by the humans. Since this looks like a CCAI paper, this looks like a human factors paper, but my point is, if you want to do human-aware AI, you better be interested in human factors, okay? So in fact, one of the things we did in that sort of work was to try to develop a nice platform where you will wind up supporting human-human collaboration in the context of Warcraft, Minecraft, okay? And more recently, actually, this was actually a couple of years back, more recently even Microsoft released a platform called Malmo platform, which also supports this kind of agent behavior in Minecraft. Okay, so we're sort of ahead of that in that case. We also did work to show that actually the kind of proactive behaviors that the planning agents are showing to the humans are in fact appreciated. Because you can, as I said, a couple of slides back, you can wind up trying to help people and irritate the heck out of them. This, by the way, is from a sitcom where some person tries to complete the other person's sentences all the time, most of the time wrongly. And that's a very bad kind of proactive assistance, and we wanted to make sure that we are not doing that. And the only way you can do it is to do controlled studies. Okay, so I very quickly went through the kind of challenges that we have looked at, the spectrum of models, and the way the planner can be useful to the human, making the behavior explicable, and also finally the fact that you want to take human factors into account, okay? And then that's a summary of the ongoing work. The summary of the talk itself, if you remember, when I started talking about the bigger picture of human-aware AI and how that is more important. And in fact, that's not sort of something that losers do. That's the thing that you want to do if you don't want to be afraid of AI. You want to create a future where you have to be afraid of robots. The only way that can happen is the robots understand how to work with us. Okay? And then I tried to give you some of the interesting research challenges that come up when you work in this. And the fact that we have papers in all these places tells you that there are interesting research problems here. So that's something that you may want to keep in mind. And then, of course, this is my last slide. These are the robots and the humans in my lab. I'll let you figure out who are the robots and who are the humans. And I am actually 16 seconds ahead of time. Thank you. Oh, just 1 second. If you have any questions, you of course can send me a WeChat message and I'll answer your question. Thank you.
Thank you very much, Professor Kamapati. I think this is a wonderful presentation, very thought-provoking, and of course a very eloquent presentation. I think you have addressed a very important problem in China, that is human-robot coexistence. I think one of the big challenges for human collaboration is for robots to understand, to interact with people who speak as fast and eloquent as you. But I'm aware of our time constraints, so since Professor Kamapati has a very nice WeChat account, perhaps you can interact with the candidates in WeChat. So thank you very much once again. Thank you very much. We do have a small souvenir. I forget to mention that Professor Kamapati is also the current president of CCAI, that is the Association for Advancement of Intelligence, or 国际人工智能促进会的主席. So that's you're the current president. Thank you very much. Really appreciate for your time coming all the way.
Thank you.
To